All right, so yesterday we finished up. As you guys were running out the door, I was screaming at you certain things. And this is where we left off. Okay? So, real quick, I just want to throw this at you. Remember, we talked about if they give you a gram or a mole of something, and then they give you and or ask about a pressure, volume, or temperature. Okay? So they give you a gram or mole, and then they give you and or ask about a pressure, volume, or temperature. We're going to use the ideal gas law, which is PV equals nRT. Now, the reason we're solving for volume in this particular one, because if we go back and look at the question, it's number 2. The volume of H2O gas released, measured at 220 degrees Celsius, 735 milliliters of mercury. Now, the important thing is we know that this is the question. Would you agree? Okay, so that is what they're asking about, is right here, and they're asking for the liters of that. Now, these two numbers right here, this is temperature and that is millimeters of mercury. Are those also for the water gas? Yes. So 220 degrees Celsius and 735 millimeters of mercury. But here's the deal. Remember, we've got to do PV equals nRT. The easy question. Do we have an R for this thing? You'll always have an R because it's a what? It's a constant. It doesn't have to be given to you, nor is it going to be told. Use this formula. Do we have a temperature for water? Yes. We're solving for volume, so that's eliminated. Do we have a pressure for this thing? Yes. Do we have an N? Now listen to the way I word this question. Do we have an N for water gas? Not yet. We do not. And here's why. Because the mole or gram that was given to us was for what specific thing? The beryllium oxalate trihydrate, or an easy way to say it, the hydrate. So what must we do with the hydrate to find the number of moles of water? No, you use stoic, right? Okay. Sir. Okay, that's a great question. Why do we use Kelvin? Let's talk. Can I answer this and then come back to that? All right, so let's do this. So we know that we have 3.21 grams of the hydrate, and we need to know how many moles of that is. And I think I actually converted it somewhere along the line. We did it? Did I? Right here. We did it right here. Okay. So 3.21 grams of the hydrate. We know the mass of the hydrate was 151.08, and then this right here is just your mole to mole. And what was the answer again? 2.06. No, yeah, that's not right. 0. Is it 0.0 or 0.6? So this is correct. So that is correct. So let me go back and double check and make sure that this is correct. So I wrote this down wrong. So let's change that. So 0.0637 moles of water. That actually makes more sense. Now, to answer your question, why did we use Kelvin? Now remember, is R a constant? If you do not remember what R is, do you have a cheat sheet? Use it to your benefit. Don't mess anything up. If you don't know, look it up. That's why they give you that thing. Don't try to depend on your memory that day, because you're going to be thinking about too much to try to remember all these numbers. So your question was, why do we have to use Kelvin? Why can't we use it in Celsius? Look at all of the bottom things in all three of our R's. It has Kelvin. Therefore, for your units to cancel properly, the units must match. That's why these three will always be Kelvin. I'm going to be honest with you. I can think of very few situations where Celsius is going to be the unit we use. But I can also tell you this. There are very few situations where they give you Kelvin. They're a bunch of jerks, and they make it harder than it really has to be. So they're saying, are you intelligent enough to catch a very simple conversion? And that's what they do. They throw those things at you, because how many students rushing through this, knowing what they're doing, forget to do something as simple as convert the temperature, and they get it wrong. Does that make sense? I think that's dirty, personally. Like, if knowing what to manipulate is enough, but having to convert pressures and temperatures on top of it is more agonizing than it really needs to be. But that's the game that we have to play with these people, that sometimes they don't treat us very fair, but it is what it is. So this is why we have to do Kelvin. Now, yesterday we left with trying to decide which one of these that we're going to be using. Now, you all agreed that it doesn't matter because liters is in both of them. That's what we're trying to solve for. True? It doesn't matter because Kelvin is in both of them, and that doesn't matter. And you all agreed that moles doesn't matter because it's also both of them. So the difference between these two is atmospheres and torr. And I screamed at you yesterday, if you know one thing, it becomes very easy. What conversion do you have to know is true? Okay? So I personally wish that this was actually written in millimeters of mercury, but it's not. It's written in torr. But if you just know that one amazing little thing, then this becomes very simple to you. Sir? Call Torricelli. I don't know. I have no idea, but I know that's what he used. Okay? So let's come back, and now let's actually plug the R in. And to be honest with you, I never use this R. I always use the other one, and you're going to see me use it quite often. But what is that value? You just had it. 62.36. So 62.36. Now, the reason I don't like this unit is because I have an easier way to remember the other one for the unit. The other unit is latum over molk. This other one, I guess I'll say torr over molk. But it's liters times torr over molk, which is mole times Kelvin. Does that make sense? Okay? The R. Yeah, that's the unit. Yep. And I'm going to explain something in a minute where that stuff comes from. Now, the pressure. Can I use the pressure that was given in the problem as is? Yes. However, to make it pretty, what would we want to do to it? How much was it? 700 and what? 35 torr. Because if you wrote mmHg, it wouldn't be as pretty. Why? The units don't match. Even though numerically, quantitatively, they match. Well, let's make them match. Now, let's look at our unit cancellation here. Do moles cancel? Yes? Do kelvins cancel? Yes. And this is where it gets weird. How does that cancel? Torr over 1 is torr. And so torr over torr does what? It cancels. So your torrs also cancel, leaving you with which unit? Liters. Leaving you with liters. Is that the unit you wanted? Yep. Okay. And so what would be your value of your volume? Before you give me the answer, let's go back and look at this thing. Do you agree that there are 3 numerical pieces of data given in the problem that we've used? That piece and those 2 pieces. What's your significant figure? Do you agree that this one is 3? This one's really easy. That's 3. But how is that one 3? It's got the decimal point. It's exactly 220. So your answer must be 3. So 3 significant figures. So what was your answer? What? Fantastic. There's your answer. Yes, sir. Yes, sir. Yes, sir. 2.7. All right. Let me double check, make sure we're all good. They have 2.67. We're good. No big deal. Now, let me teach you where these units come from. We cool with that? So, I know we've talked about this a little bit, but I just want to make sure that we're all good. So we're going to talk about this thing called STP. And what does STP stand for? Standard temperature and pressure. So our standard temp is kind of weird. These are not standard conditions. These are standard temperatures. Does anyone know what the standard temperature is? And it's a sheet up there on that box. 0 0. Or 273. I've really got to fix this thing. What's wrong? You sit over there. Now, let me ask you something. If this were standard room conditions, would you enjoy it? That's 32 degrees Fahrenheit. That's not very comfortable, okay? Now, that's not standard room conditions. This is just standard temperature and pressure at STP. Does anyone know what your pressure is? Okay, 1 atm, which is also equal to 760 millimeters of mercury, or what? Torr. So this is STP. So here's how they figured out these constants. Everybody cool with that? Not O-torr, or torr. 1 atm equals 760 millimeters of mercury, or torr. Cool with that? All right, so let's look at this. Then we've got PV equals nRT. Well, if we want to know what R is, can we isolate it? What is R? No. Isolate it in the variables. Please do not mess up basic algebra. Every year I have a situation where people lose stupid points because they can't rearrange a basic linear formula. Don't be that person. Be smarter than that. Now, so if we want to know what R is at STP, just plug it in. So let's do two of them. We're going to do two calculations. The first one we're going to use is we're going to use 1 atm. Okay. Also, I missed something over here. My bad. STP is at 1 liter and 1 mole of a gas. Also forgot that. My bad. So I should have thrown that in a second ago. So STP is normally at 1 liter and 1 mole. Nope, I'm stupid. I'm glad I looked, because I knew that didn't sound right. 22.4 liters. It is very different than 1. So let me say this so it'll make more sense. If I gave you a gas, any gas, and I gave you 1 mole of it, just throw this out there, how much would 1 mole of hydrogen weigh? That's a trick question. Why? Because what's hydrogen? Hydrogen's a... Thank you, sir. Chance, why? Very good. It's a trick question. So if I gave you 1 mole of hydrogen gas, it's 2.02 grams, right? Because hydrogen's diatomic. Throw this at you. What if it were nitrogen gas? 28.02, because nitrogen is a diatomic. Okay. What if it's water gas? 18.02. So does that make sense? If I gave you 1 mole of any of those gases, and it was at 0 degrees Celsius and at 1 atm, how much room would it take up? 22.4 liters. Is that a lot? Yeah. How many 3 liters would that be? Come on now, 3 liters. At least 7, right? 7 point something-ish. You've never seen a 3-liter Coke? You need to get out more. They make 3 liters. It's not used for like individual consumption. It's used for parties. For like birthday parties. That's true. All right, so let's go back to this. So volume at STP, and again, we're solving for R at STP. This is what we're calculating, and I guess I could write it right here. So at STP. So we know that the volume is going to be what? 22.4 liters. So at STP, how many moles would that be? 1 mole. What would your temperature be? Very good. Now, here's the next interesting part of this. Hold on. If you look at all of these units, how many of them cancel? None of them do. So would you agree that I would have liters times atmospheres over moles times Kelvin? Hang on, nobody said it out loud. Everyone do that math real quick. 22.4 divided by 2.7 or 273. Sure. Amazing. Rounding. Does that make sense? So that's where the R's come from. Now I'm going to do this. Go ahead, Dustin. That's through experimentation. They said I'm going to give you 1 mole of hydrogen gas, which we know weighs exactly 2.02 grams. They dropped the temperature to 0 degrees Celsius, and they put 1 atm of pressure in the container, and it expanded to 22.4 liters. It is a weird expansion, but it's at STP, yes, and all of them do. It is weird. All gases, doesn't matter what gas it is, expands to 22.4 liters if you've got 1 mole of it at 0 degrees Celsius and 1 atm. Sir. Not liquid, gases. Okay, so I see what you're saying. You also have to take freezing points into example. Pressure. Okay. Now, if we go back to this, if I did this again, one thing I could change at STP, could I write 760 torr? Is it still 22.4 liters? Is it still 1 mole? Is it still 273 degrees Kelvin? Now, without even doing the calculation, I bet you could possibly tell me what that value is going to be. .6236. So that's where it comes from. So does that help understanding now what R is? Okay. So my whole purpose of showing you the gas R, and again, I've got 2 questions. How do we know these 2 are the gas R's? What 2 properties in the unit tells you that it's a gas? Pressure and volume. Okay. You've got atmospheres and torr, and then a volume. How would you know the top one is not a gas R? Joules, and joules is specifically used for what? Energy. And we'll talk about energy R enough later, but we're just focusing on these 2 right now. So does that make sense? Basic stuff, right? Don't let it overwhelm you. We're all good. We're all good. All right. Any questions? But is logic coming through? Does it make sense? As long as it makes sense, we're good. That's okay. We've got plenty of time for you to remember it. All right, so the next question. Answer the following questions that relate to the chemical reactions. Iron 3 oxide can be reduced with carbon monoxide according to the following equation. Have we talked about this yet? Oil rig. So what it means when it says can be reduced. Reduced means what? It gains electrons, but the charge does what? The charge drops. Remember when we were doing oxidation numbers a long time ago? This is a really good, actually, I love this question now that I'm actually thinking about it. Oxidation numbers. Love this question. Those of you that have me, you better rock and roll through this. I mean, you've heard me say this 100 times. Is this compound charged or neutral? Set it equal to what? 0. Is the metal present? What's the oxidation number of the metal? How do you know it's 3? You reverse crisscross. Okay. What do you do with your numbers going down? Multiply. What is positive 3 times 2? Positive 6. What do I need to make it neutral? Negative 6. What is negative 6 divided by 3? Does that make sense for oxygen? Look at that. It is not always. In most cases. However, we could have done it the opposite way. We could have said Fe2O3. Neutral or charged? Neutral. Do you have fluorine? No. Do you have oxygen? Oxygen is? Negative 2 times 3 is? Negative 6. What do you need to make it neutral? Positive 6. What is positive 6 divided by 2? Same difference. Okay? Yes, sir. Yes. Ma'am. 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 Jamila? You good? Yeah, that way you can find the charge on the metal. Because remember, all metals have specific charges, always. You could. Let me throw this at you. Hang on. Then you run into an issue, right? So let's just look at this one. Neutral or charged. Set it equal to. Is a metal present? Who is that metal? What's its charge always? +1. What is positive 1 times 2? Do we have fluorine? I'm going in a specific order, and if you want to get this order, I'll give you the sheet to be able to do it. Is fluorine present? Is oxygen present? What is oxygen? -2. What is -2 times 4? -8. In here, there has to be a number. This whole thing has to be equal to 0. What number has to go in there to make it 0? +6. Is there anything to divide by? No, so sulfur is +6. I know it looks like a lot. We've done this so many times that it has become repetitious. It's something that is very simple. There are really 3 rules you've got to memorize. That's it. Actually 4. But one of them is easy. The first rule is that thing neutral or charged? How do you know that it is neutral by your eyeballs? Do you guys hush. I'm talking to these 4 in the front. And Elizabeth. How can you tell with your eyeballs that this is neutral? Very good. If it's charged, it's got to have a plus or a minus. True or false? True. So it's neutral. If it's neutral, you have to set it equal to what value? 0. If it's neutral, it's 0. Let me give you another example, and I'm not going to run through it, but I just want you to see it. What if it were PO4 3 negative? Is this neutral or charged? That's charged. If it's charged, what do you then set it equal to? That's rule number 1. That's really easy, right? Rule number 2 is, do you know the charges of metals? If it's in group 1, it's 1. If it's in group 2, it's 2. If it's a transition, can you reverse crisscross to figure it out? That's your metal. The next 3 you just got to memorize. Fluorine, would you agree, is the most electronegative? So it is always what? -1. It carries its charge. Does that make sense? For your purposes today, and I'm going to give you a sheet later, there's one exception to it. Oxygen is 99% of the time -2. Is that also its charge? Okay. Hydrogen is the next one that you've got to know. And it's got 2 weird exceptions. But for your purposes today, it's +1. Is that also its charge? Yes. Does that kind of make sense? So if we go back and we do this one, you've already told me it's -3, right? Okay. What is, you don't have a metal, you don't have fluorine, but do you have oxygen? And oxygen is -2. What is -2 times 4? -8. This is where it gets a little weird. There's got to be a number to make this side match that side. +5. Is there anything to divide by right there? Nope. So that is the oxidation number of phosphorus. So it's a simple, basic math, algebra. You just got to know really 4 rules. Is it neutral or charged? What the metal is, fluorine, oxygen, and hydrogen. Okay, so 5 rules. But they're really simple. Yes, ma'am. Yeah. That would have helped, wouldn't it? My bad. Forgot you left early yesterday. Yes, sir. Bingo. What happened after it reacted? That's why. That's so we're fixing to look at it. So Justin, you asked what reduce means. Well, and I'm glad you asked that. That's why I said I kind of paused and I said, no, I love this question because it led me into that discussion. And here's where we can then add to this. Do you agree that iron as a reactant looks completely different as a product? So it went through some sort of chemical change, right? One, remember there were 5 signs of a chemical reaction? One of them was oxidation. Okay, what's the opposite of oxidation? Can you have one without the other? Say no to that. So, and I never told you that, so that was a little small white lie. So when I told you one of the signs of a chemical reaction was oxidation, what word did I also leave off? And reduction. But now that you know that, it's just one little thing that we can add to the knowledge base. So if something oxidizes, what else has to happen somewhere else? Something's got to reduce. So you just told me a minute ago that this oxidation number on that iron was what? +3. I'm just talking about iron. Just looking at iron. Here's the cool part. Look at the iron on the other side. First question, is it neutral or charged? Neutral. Set it equal to 0. What's it with? So who's it sharing its electrons with? No one. Pure elements are 0. So let me ask you something. Iron went from what to what through the reaction? I'll come back to that. It went from 3 to 0. Did that reduce? It dang sure did. That's reduction. There's not a question involved in this. The way the question was worded is what he pointed out. It says iron 3 oxide can be reduced. Was iron reduced? Yes. Now, we're not going to get into it. However, was something oxidized? Would you like to see what was oxidized? What do you think it was? Well, it's carbon. Let's look and see how we can tell. Yeah, you were right. Look, look, look. Do you agree CO is the reactant and it went to CO2 as the product? Would you agree with that? It should be kind of obvious. Equal to 0, true or false? Is there a metal? Is there a fluorine? Is there an oxygen? What is it? -2, -2. That makes carbon what? I need +2 here, +2 here. Would you agree with that? Okay, over here. Neutral or charged? Is there a metal? Is there a fluorine? Is there an oxygen? -2, -2 times 2 is? Would you agree that's +4? You just told me that iron reduced, which means what happens to its charge? Did carbon change? Did it go up? So did both occur. That's oxidation reduction. Bingo! Redox. Okay? Go ahead, Trevor. This carbon going from a +2 to a +4 is oxidation. Oxidation is a loss. A loss of what? No, let's finish that out. It's weird. I know it. Okay, how about this one? How about Leo says Ger? Loss of electron. No. Loss of electrons is oxidation. Leo. Ger. Gain of electrons is reduction. Oigril. Spell it for me. Oig. In real? That? Oigril. Oigril. Oh. All right. So here we go. We've got a 16.2 liter, but you know, I really think it's important because let's be honest, those types of questions. So I mean, I could add a part number 4 to this, and the question could be, what does the oxidation number of iron go from and to? And that's literally the question. Or that could be part number 1. So you see what I'm saying? So those types of questions will be coming your way, and the more you see it, the better you're going to get at it. I know it's like hitting you with a sledgehammer the first time you see it, but if you pick up on the little things now, when you actually get to when it matters, you're like, I got this. I can run through this. Okay. So we have a 16.2 liter. Now, what type of measurement is liter? It's a volume. Now, I'm going to be honest with you. I do this occasionally when I'm taking like certified, bona fide, difficult tests. I did this in college. Whenever I saw numbers, I always labeled what type of measurement it was. That was just a habit that I got in, and it really helped me out. So if it's something that you guys get in, it may help you out and benefit you. So I've got a volume, okay, a volume sample of carbon dioxide at 1.50 atmospheres. And atmospheres is what? That's a pressure, so I know I got a pressure. And then 200 degrees Celsius, and what is that? That's temperature. So let's look at that for just a second. Do you agree they gave you 3 variables for 1 reactant? Right? They gave you pressure, volume, and temperature. What does that sound like we may have to use? The ideal gas law is combined with 15.39 grams of this. So do you agree? All right, so this is just the mass, and we know that that's the other reactant. Now, I'm going to just throw this at you, and let's see where it lands. If you don't know, we're cool. That's fine. Did they give you starting amounts for both reactants? They gave you something for CO, and they gave you something for Fe2O3. Is that both reactants? Potentially, I'm not telling you we're going to have to do this. Potentially, what could you might have to solve for? The limiting reactant. Keep that in the back of your mind. I'm not telling you we are, just telling you there's a potential. Sir. Yes, absolutely. Is that on there? Yes, reactant and Oh, it is on there. Sorry, I didn't even read that far ahead. All right, so we know where we're going, though. Number 1, I like this question because it forces you to do a little bit of the work before the problem gets challenging, and here's why. My question to you is, let's just go ahead and look at number 2. What is the limiting reactant? What is the cheat for limiting reactant? Moles over coefficient. Look at question number 1. How many moles of CO are available? Do you agree that go ahead and gets you in that mole category? Okay, so we'll talk about this in a second. Also, we know we got to do it, but what are we going to have to do with that 15.39 grams of iron 3 oxide? We got to get it to moles. I will tell you this. I've noticed the past trend in the exam of the past few years. They've gotten really good about giving molar masses on the test, so you don't have to calculate it. Their theory is you should know how to do it. That's a foundational skill. We're not going to waste your time or cause you to potentially make an error to miss the problem. Does that make sense? If you, for some reason, mess up the mass, that's going to cause your answer to be wrong. Their theory is we would rather know can you do the conversions versus mess up a simple mass calculation. So I've noticed, maybe not all of them, but some of the problems actually come with a mass built into it. So let's look at number 1. How many moles of CO are available for the reaction? So let's think about it. What were we given about carbon monoxide? We were given a volume, a pressure, and a temperature, and we were asked about moles. Can we solve moles based on the 3 things we were given? Yes. What can we use? Pivnert. We have all of them but the N, right? So we have PV equals nRT. And this time we're solving for which variable? N. So we're solving for N of CO. Would you agree? Okay. So again, please, this is the easy part. Don't mess this up. What is N isolated? What's the formula? Thank you. You would be shocked, maybe you wouldn't be shocked at how many times I have seen in the past RT over PV. Like shocked at how often that happens. And it may be just a simple brain fart, but it can't happen. Yes, ma'am. Okay. I didn't. I apologize. Okay, we're good. We'll get them out. Yes, sir. Yes, but why would you do that? That would be a bad idea. Okay. Now, help me out because I'm not looking at it. What's the pressure that was given? 1.50 ATMs. What was the volume? 16.2? 16.2 liters. Now, here's an important question. What was the major differing factor in our R's from earlier? Torr. One was atmosphere, one was torr. Which one are we going to use this time? We're going to use atmospheres. That's the one you're going to most commonly use. So it's 0.0821. Okay? So, and again, if you do not have this number memorized, is it a big deal? No, you just use the cheat sheet. 0.0821, and it's latum over molk. Now, honestly, in every piece of literature that I read that comes from the AP exam, they don't even know, like, the people that grade this stuff and that teach this stuff, they don't know why College Board leaves it as 0.08206. They think they should just go ahead and make it 2-1, just because the extra 0.6, what does it really change? No. It's real, like, it does make a difference, but it really doesn't when we're working with just small fractions of stuff. Okay, so they have said this is perfectly appropriate. Prime example: if I ask you to convert Celsius to Kelvin, what do you add or subtract by? It's 273. Do you know it's technically 273.15? But we don't have to do that. Okay, that's something that they've also accepted as we're just going to knock off the 0.5 and call it even. Okay, yes, sir. That's a great question. When you're practicing this stuff on your own, um, just for practice purposes, no. But for exam purposes, absolutely. So, personally, it's a good habit to get in. I would say yes. But I'm not going to mark it wrong on a worksheet if you don't do it, but on a test, I will take a point off. Okay? Now, temperature. Because of the R unit, what must your temperature unit be in? Is that a good thing or bad thing of the question? It's bad. So what do we, it's 220, right? So at, 200. So 473 Kelvin. Okay, so 473 Kelvin. And again, I always like to go through and look at it. Do our units cancel? Atmospheres cancel, liters cancel, and Kelvin cancels. And this is where it's kind of weird. So we have 1 over 1 over a mole. So what's your unit? Mole. How do you get a fraction off the bottom? So would you agree that this is equal to 1 times mole over 1? Well, what is that going to then be? A mole. Just want to make sure we're good with algebra. Mole of CO. Yes, sir. That's a great question. It is degree Fahrenheit and degree Celsius. It is not degree Kelvin. It is straight. Don't ask me why I didn't make it up. It is straight Kelvin. Okay. I don't know why they took the degree off of it, but I know that it is not degree Kelvin. It is Kelvin. Dustin, I'm going to come back now. Let me think about this. Do you agree that pressure is the intensity of a collision? If you take gas molecules and you put them in a flexible container, a balloon, and you increase the intensity of their collision, what's going to happen to the size of that balloon? It's going to get bigger. Does that help? Yes. Yes, sir. All right, I just kind of went through a basic algebra skill. Let me put it to you this way. This is a lot easier. What was the question? Read the question. The first 4 words. Stop right there. Bingo. You don't have to worry about all that other junk. You know your unit has to be moles. And you know moles is in there and everything else cancels, roll with it. And again, that's the easy way to think about it, but I like to sometimes just show, all right, how did it become that? Yes, sir. Yeah. Yes. Yes, ma'am. All right. Well, I don't have two Kelvins. Kelvin is a part of one of my units, and I have to have both of them there to cancel them to get rid of them, right? Because my final answer must be in moles. And so if you think about it, I have an atmosphere here, and it goes away. An atmosphere here, it cancels it out. I don't have it anymore, right? I have liters here, cancels. Liters here, cancels. Kelvin here cancels. Kelvin here cancels. So the only thing left out of all of your units is a mole. And the first three words in that question is, how many moles? It's left. Does that help? Okay. Anybody got a value for this? 0.626 moles of CO. Huh? No. All right. So the next thing. The next question says, what is the limiting reactant for the reaction? Justify your answer with calculations. Now, the good news is we've already got moles taken care of, and we know that the limiting reactant, the LR, is equal to moles over the coefficient. Now, so let's go ahead and go back to this part right here. Can we go ahead and take care of this one? What do we need to do to that number? Why are we dividing it by 3? Fantastic. Look at the coefficient. So we're going to divide this thing by 3, and somebody help me out with that answer. 0.209. Now again, is that number, that 0.209, useful to us at all? It is simply used to identify the LR. And based on its value, when you compare it to the other, how do you know which is the LR? The least amount. Okay? Now, this next part is the simple part. They give you the other reactant. What type of measurement is the other reactant given in? Grams. Okay, so I'm going to kind of step right here. And it is how many grams? 15.39 grams of Fe2O3. Are you capable of doing this one? You better be by this point. The hardest part of this problem is calculating what? The mass of the compound. That's the hardest part. So 55.85 times 2 plus 16 times 3. Anybody got that? 159.7 what? 0. I just want to make sure it was 0. And that's going to give me a certain number of moles. Dusty, you got that? Or Chance? Yeah, 15.39 is your original mass. 0. So that right there, that's right. Is it 0.0 first of all? 937. Because you're right, it is 4 sig figs. 37 moles of Fe2O3. Okay, very good. So if we're trying to determine the limiting reactant, very simple, divide by the coefficient. What is the coefficient of this one? It is 1. So we're going to divide this by 1, which is equal to the, and this is a genuine question, I really don't know, is there a symbol in math that means the same thing? That's our new sign. It's equal to. I don't know. Yeah, that's approximate. Yeah. All right, so my question, that means equal to. It's equal to that part. There's no difference. I want a symbol that means I don't have to write that whole thing down again. But if you're really doing this, you need to show it. Does that kind of make sense? So according to our rule, we're just using an identifier. Which one is now our LR? That's our LR. That's our limiting reactant. Because it's less than. .09 is less than .2. Okay, so let's go back to the question. Question 3. How many moles of Fe are formed in this reaction? Now, so I got to go from my reactants to my products. So I've at least got to use what? I've got to stoich it, right? I've got to go from my reactants to my products. Which reactant am I going to use? The Fe2O3. Why? It's the limiting reactant. Okay? Now, I like this problem. It's really simple. Why? What unit are they wanting it in? Moles. How many steps is it? It is 1 step. Why is it 1 step? You've already found the moles. Spectacular. So this is really easy. I love this problem. So 0.096, what is it? 637 moles of Fe2O3. And we're going to go mole, and I promise I'll move in just a second. Fe2O3 to straight moles of Fe. Hello. Hello. It's an alert. It's an email alert. Now, so what is your mole to mole ratio? It is 1 to 2 or 2 over 1. So what do you do to that purple number? Double it. So 0.18. Okay, that's right, at 19. 0.19 what? 27 moles of Fe. So we started out with a really, really difficult question about what does reduction mean. And we've got it down to you using the ideal gas law, calculating N. Then we found the limiting reactant, which you've already done before. And then look how simple of a mole-to-mole change that was. So it can start out somewhat kind of complicated, but you guys have done every bit of this before. The wording is what's scary. You see all these numbers and all these symbols and all these letters and words and formulas you've never seen before, and it's intimidating. But the chemistry of it, you've all done before. Nothing's different with the chemistry. It's all the exact same. All right, so here's what we're going to do. Yes, ma'am. Yes, ma'am. You can. You can. But the ideal gas law is so much easier. So much easier. I don't even want to show it to you because it will confuse you. And it's not worth the... Say it again? Oh my gosh, yes. No, you have to do all sorts and kind of conversions and plug it into some stuff where the ideal gas law, you've got 5 variables. You need one of them. One of them is a constant. They give you the other 3. Rearrange that sucker, plug it in and go. Right? Does that make sense? It's a lot easier to say, okay, how do I get from here to here doing all of this stuff? You take a formula, you rearrange it, basic algebra, you've been doing it your whole life, stick that sucker in there and go. The hardest part about the ideal gas law is making sure that your R matches your units. That's the most challenging part. Okay. All right. R is just a constant. It's just exactly. It's R. We're gonna talk about Q's. We're gonna talk about K's. There's a lot of K's. KQ's. You've been in here a few times for those, haven't you? Okay. That's right. All right, so let's look at B. Now, Mason, you made a very observable point here. Why didn't they just make this a completely separate problem? You're going to find out that within one problem, they do multiple concepts. Okay? You may have one problem, question 3, and the first part of it may be an electro problem. The next 2 parts may be a thermo problem, and the next 2 parts may be kinetics, all in question number 3. But somehow, some way, they tie all of it together. And by the end of the year, you're going to say, yep, 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 I know how to do all of that, and just go right through it. Okay? And honestly, I like those kind of problems because it gets you to see big picture. You don't see things as individual things. You see how it all interconnects. So, like when we start talking about the equilibrium constant, we're going to do it probably around Thanksgiving to Christmas. When you understand the equilibrium constant, you're thinking, what does equilibrium have to do with electrochemistry, with thermochemistry, with kinetics? All of it ties back together once you learn that one part. And it's really cool to see it all tie back together. All right, so B, in a reaction vessel. Guys, all that means is a beaker, a flask, something where a reaction takes place. That's all it means. It's a vessel for a reaction. Okay? Like a cruise ship is a vessel for fun. It just makes them sound fancy. 0.600 moles of, what is that compound? Nitrate. What state of matter? Solid. And 0.3 moles of, what is that stuff? Very good. How do you know this is an acid? It's got an H and it's aqueous. So what they're doing is mentally, think about this. They have this solution of acid and they're fixing to dump some barium nitrate in it that's solid. We cool with that concept? That's all they're fixing to do. They've got 0.3 moles of the phosphoric acid and they've got 0.6 moles of the barium nitrate. Are combined with deionized water. Now, why is it important to understand deionized water? There's nothing in it but H2O. Now that we have read this, what looks very, very odd to us about the reaction given and the wording of the problem? There's no water in the problem. But what does AQ mean? Dissolved in water. The AQ makes it be understood that water is present in this thing in some capacity. Yes, sir. Okay, that's actually a really excellent question. So we take barium nitrate solid and phosphoric acid and we combine it with water to reach a final volume. So what does that tell you? Now I love this question because you're observant here. How do we go from this thing to that thing? What does it tell you about barium nitrate? It dissolved. So this thing is soluble. That's very, very good observation skills right there. Any other questions? I saw another hand. Justin? Yes. 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 Okay. The reaction represented below occurs. So we've got barium nitrate plus phosphoric acid, and then what's that next product? The first product. Barium phosphate, and what do you notice about the solid? Sorry. What do you notice about the state of matter? It is a solid. What do we call a reaction where we take two aqueous things and a solid comes out? Very good. This is a precipitate. And whenever we start learning our solubility rules, you will know that that is actually a solid precipitate. Now, I need to say this because every year it kind of gets people. When you pour those two things together, does it fall out like a rock in a big, huge clump? No, it's very, very, very tiny, like sandy particles that just float. Okay? So make sure you know that it's not a clump like a rock. Yes, sir. It's a solid. No, it's a solid precipitate. You could, I mean, really, it's the Department of Redundancy department. Okay, you're saying the same thing twice. Did you follow that? The Department of Redundancy department. Okay. So that really solids are precipitates and vice versa. So the reason we call it a precipitate is because it came from two solutions. That's what makes it precipitate. Your Department of Redundancy department. Okay. Now, what is that second product? Very good, nitric acid. Okay. Now, calculate the mass of barium phosphate that is formed. Okay, Trevor, you stated that we have to find the limiting reactant. Why? Why, Trevor? Would you agree that that's true? Okay, so here's the deal. Do you have two starting amounts? Then how in the world are you going to get to that product? You got to find the limiting reactant. Hold on one second. Hold on. So here's my question. We know now that we've got to find the limiting reactant. And again, the trigger that tells us find the LR is the fact that two starting amounts are given, right? So we don't know which one we have to pick. That you said a minute ago, this is really easy. Why? It's already given in moles. Would you agree with that? So here's the deal. Since it's already given in moles, we divide both of them by their coefficients, which the barium nitrate is divided by 3, and the phosphoric acid is divided by 2. So what is 0.6 divided by 3? 0.2. And what is 0.3 divided by 2? Okay, 0.15. So obviously, which one is less? The phosphoric acid. Okay, right? So here's what we have to do now. We have to then convert our moles of phosphoric acid to what? Beryllium, no, not beryllium, barium phosphate. The grams of barium phosphate. Now, this is a reasonable question. How do you know you have to go to grams? It says mass. I just want to make sure that we're all on the same page there. So we've got 0.3 H3, and I forgot the word moles. Yeah, actually, I'm glad you said that. 0.300 moles of H3PO4. Why do I keep doing that? And then we've got moles of H3PO4 to the moles. And I'm going to be really lazy right here, and I'm just going to write the word solid because I really don't feel like writing that whole thing out. So we've got moles of the solid to grams of the solid. Now, I'm going to help you out. If you've already calculated it, I'm sorry. But the mass of barium phosphate is 602. 602. That's all right. We're good. And what's your mole to mole? 1/2. And so the mass that you would come out with is 90.3 grams of barium phosphate. That's your molar. That's your amount of grams. That's interesting you asked that. That's what we're doing tomorrow. All right, number 2. What is the concentration in moles per liter of the nitrate ion after the reaction reaches completion? Now, this is where it gets kind of strange. Okay? So, you've seen this kinda, but not really. So 0.600 moles of barium nitrate. Now, here's the important part. Do you agree we have barium nitrate? But we're trying to get to what specific part of barium nitrate? Nitrate. Do you remember that whole thing a while back when I said an atom to molecule ratio? Well, this is an ion to molecule ratio. Are atoms and ions kind of the same thing? What's the difference between an atom and an ion? That's it. Same exact concept. So, if we have moles of barium nitrate, now let me ask you something. How do I know that that is for sure on bottom? I've got to get rid of it. Now, if you're in moles of something, can you convert to moles of something else? Yes. Now, the problem that makes this a little weird, since you've never seen it before, is that there is no way to do this with the coefficients. But remember, we're trying to do moles of a specific ion within a specific compound. So is this just like the atom to molecule ratio? So for every one barium nitrate, how many nitrates were there? Fantastic, there were 2. And then there were 2. Now you guys are intelligent enough to know that this is what? 1.2 moles of nitrate. I hope. Sure, 1.20. Now, this is the next part that we're going to get more in depth tomorrow. And this is why I love this question being last, because it catapults us into tomorrow. The question is not how many moles of nitrate remain. It says what is the concentration in moles per what? Liter. So my question is, do you have a mole value? Do you have a liter value? Now read right here. Are combined with deionized water to a final volume of 2 liters. So what do you do with your moles? Fantastic. So we've got 1.2 moles of nitrate divided by 2.0. Is it 2.00 or just 2? 0, 0. So 2.00 liters. Well, what is 1.2 divided by 2? Now, if you want to write it like that, is that technically the correct unit? Yes, but is it the most accepted or appropriate version? What else could you write it like? Or molar. Capital M stands for molarity. We're going to do molarity so much. Don't get hung up on this yet. Just, yeah, sure. So here's the deal. You know what this means. No. Molarity is mole per liter. You have moles, right? What was the volume after it finished? 2 liters. Moles divided by liters. Okay? Concentration equals molarity, which equals a capital M. Trevor. Yes, sir. Yes, sir. And I know the question says after the reaction completes. And that's a very good question. Now, what I want you to look at is, do you agree that nitrate is in both the reactants and in the products? But the only place we have numerical quantitative data is for which one of them? The first one. Now, this is where it kind of you have to make a connection. Based on the conservation of mass, if you've got a certain amount of nitrate on one side, how much do you have to have on the other? The exact same amount. So you can use that tie together, that if you know something about the one side, it has to also be true about the other side. So does that help? If you wanted to convert, well, you couldn't do the limiting reactant because the nitrate is in excess. You with me? Yeah. Yes, sir. That's exactly what it's referring to. So this right, and this is something we'll see a lot of, and I'm glad you asked that question. What does anything x to the negative first power, what does that mean? That means equal to 1 over x. So if you've got moles times liters minus 1, what that literally means is moles over liters. That's a great question. Great question. Can I show you something else? As a matter of fact, it's on that sheet that you guys have been the constant sheet. When you look at the R, yeah, it's liters times atmospheres. Wow, that's a really weird M. Times mole to the negative 1 times Kelvin to the negative 1. That's how it's written on that sheet. And let me tell you why they do it this way. It's because if you're typing this up in a digital document format, it is really hard to make it a fraction. It's really hard to type that like this. Liters times atmospheres over moles times Kelvin. As far as digital formatting, that's a difficult transition. Okay? Sure. I agree with you. I'm not saying that it's more appropriate. I'm just telling you why they do it that way. Okay? Any other questions? It's telling you to stop. Your body has those defense mechanisms built in. When something's hot, it says, ow, let it go. So if your tongue is bleeding because of the products you're eating, it's probably telling you to stop eating those products.